So the good thing of the logarithm is that it makes exponential trends linear, and it makes multiplicative seasonalities additive. So multiplicative seasonality, just briefly, this air passenger series has multiplicative seasonality, which means that with the level, kind of, if the level is low, the seasonality is small, and then if the level is high, the seasonality is big, and that's multiplicative seasonality. And because STL is an additive decomposition, you need the seasonality to be additive and not multiplicative. And one way of doing that is with a logarithm. The logarithm also stabilizes the variance, right? But the downside of the logarithm is that it's a very strong transform. And the problem of that is that small changes in that transformed space, where you fit your model and you try to minimize these differences, then afterwards you transform back to the original scale, and then suddenly these small differences are huge. So that's a bit dangerous. So there is this Box-Cox transformation, which is kind of a generalization of the logarithm with a parameter lambda. So if lambda is 0, you just do the log. And if lambda is not 0, then you do this power transform. So if, in particular, if lambda is 1, it's basically the identity. You just subtract a 1 from your series. And if lambda is other values, then yeah, you get something in between identity and a logarithm. But now you have this parameter lambda that you need to choose, and this can be actually difficult. Yeah, so let's have a look at what happens if we log transform our air passenger series. You see now this multiplicative seasonality is gone. It's now an additive seasonality, which means that these seasonalities, they are all now all the same size, no matter where you are in terms of the level of the series. If we difference this now, now we really got rid of the trend and of this changing variance. So now the only thing that is left is a seasonality.